This is the berkeley-scf Spark workshop on Friday, November 7th. Okay, so let's go ahead and get started. Is anybody not signed in? Okay, there's a sign-in sheet here. Circulate that. Okay, so let's see, a few preliminary items. I'm going to be working off of this HTML document, which there's a link to it from the SCF webpage under computing/Spark. It's also in the GitHub repository that is referenced from this webpage as well, and the underlying markdown document used to create the HTML as well as some other auxiliary files are also in here, so you have access to all of those materials. So the idea here is I'm going to talk today about sort of the very basics of starting up a Spark cluster and just doing some very basic reading in data and doing some basic data processing, sort of pre-processing kinds of things. And then next Friday I'll focus more on working with statistical models and doing some optimization and model fitting. And depending on sort of what people's interests are, I'm also welcome to modifying the material for next week. So if you have some things after having seen what we do today, if you're interested in some particular aspects of things, just send me an email, let me know what you're interested in, and I might be able to modify things. And I'm also interested if there are people who are thinking about fitting particular kinds of statistical models or doing particular kinds of data processing, and I don't cover that here, or you don't see that in the material that I have prepared for next week. I'm happy to have more discussion next week as well, and I suspect that there are people in the room who know more than I do about various aspects of this, and we also have an expert in the room, Jay, who maybe you can raise your hand here, who's from the AMP Lab, who's one of the developers of Spark. So at various times, I'll try not to rely too heavily on him, but at various times I might, if there is a question that I'm not sure about, I might send it his way. And anybody else, like I said, please weigh in with questions, or if you have some experience with a particular aspect of this, pipe in, particularly if I'm going off in a direction that doesn't seem quite right. So let's see if I can. How do I get this? No, I'm sort of forgetting how big this was before. Okay. Okay, so this was a little bit of preliminary work. We're gonna work with a running data example, which is sort of a famous example in what statisticians think of as big data, which is about 10 gigabytes of data from the federal government on airline departure delays. So this is the famous ASA Expo data. It goes from 1987 to 2008, and it's basically information on every flight, I think it's just domestic flights, every flight in the United States from over that 20-year period, what the airline was, what the airports were, how much of a departure delay there was, how much of an arrival delay there was, all sorts of things like that. The demo, all of this demo is based on processing the full data set, so that's what's in the HTML. What I'm actually going to try and do in real time is just work with 3 years of the data so that we're not sitting here for 5 minutes while it's doing various processing. So I'm engaged in a bit of a high-wire act here, which is trying to do a live demo with a modestly large data set and in a distributed computing context, and we'll see how well I succeed. So I'm just going to work with those first 3 years. Okay, so the other question, I have a question for you guys, which is how many of you are reasonably familiar with Python? Okay, good. So a fair number of you. For those of you who are not all that familiar with Python, I don't think it'll be a big deal. You won't necessarily understand the exact syntax I'm doing. I'll try and give you some signposting along the way to give you a sort of basic indication of what the different pieces are doing. But if you get the big picture of what I'm doing and the sort of basic context and the basic steps, there's also an R interface called Spark R. As long as you sort of know what the big pieces are and what the keywords are to do the basic steps, I think you'll probably be able to translate this into R fairly readily. So that's part of the goal here. Okay, so the other thing I want to comment on here is I'm not proselytizing for Spark here. There may, in fact, particularly if you're not working with huge data sets, there may be a better way to do some of what, in fact, there is a better way to do some of what I'm doing here because I'm not going to be working with a very big data set. So the goal here is to get you familiar with this idea of MapReduce, the Hadoop distributed file system, and with using Spark, such that you could evaluate in a knowledgeable way whether it will actually solve the problem, solve the kinds of problems that you want to solve. And at the bottom of this document, I have some other tips and sort of tools that you might look into, particularly if you're an R user, for dealing with at least modestly large data sets. Okay, so why don't we jump right in? Are there any questions at this point? Okay. All right, so a little bit sort of the big picture here. Just I think a graphical representation might help because I'm going to be sort of moving around between different windows. So you can think of this box as being this laptop here. I'm going to start up, or actually I already did start up, an Amazon virtual cluster of 13 virtual machines, 13 instances. So from the command line on my laptop, I started up that cluster of 13 machines. Those are represented here. Here's the master that I started up, and there are going to be 12 workers that I started up. Each of these is an individual Amazon EC2 instance. You can think of it as basically just a virtual Linux server. And if we look here, this I did a couple hours ago because I wanted to get it out of the way. So the starting up of the Amazon cluster and the installation of the Spark software on all of the nodes of the cluster takes a while, like 10 or 15 minutes. So I did that in advance. That was done by basically downloading the Spark, the tarball, the zipped up Spark materials, untarring it, unzipping it. I didn't actually install it. I just unzipped all of the files. And then there's this Spark EC2 script here that's in this directory that I unzipped. And that script will basically start up the 13 Amazon nodes, and it will install all the software on those nodes and set up the Hadoop distributed file system. Okay, so that's what I'm saying here about unzipping the Spark software and then setting up some environment variables, in particular Amazon credentials here. And then running this line of code here in the HTML, which is the same thing that is indicated here in the actual Unix shell here. And so once you start that running, this is on my laptop, it's going to give you information back that says basically this, that it's creating a security group. Oh, I don't want to go into the details here, those details, but it's basically starting up a cluster. It is launching a particular base Linux image. 13 instances from this base Linux image. So 12 slaves or 12 workers and a master. This -w, which I filled in, I think the value of my Unix environment variable wait time is 300 here. Yeah, it must have been because that's what it says here. The reason for this wait time is basically this script needs to basically go and tell Amazon to start up these nodes, and then it needs to basically wait until the nodes are started and ready, and then it needs to go in and install all the software. So it has to have this delay of this wait time in order to be able to do that. Yeah, question? Oh, no, you're just, okay. So this is just starting up the Amazon instances, and then there's waiting, and then there's going to be a whole bunch of stuff it needs to do. It basically needs to set up the networking between all of these virtual nodes. It needs to, let's see if there's anything else useful to say here. It needs to basically copy a bunch of files over to all of those nodes so that it can then unzip them and then install all of the software. So there's all of setting that up. There's basically setting up the disk on all of these instances. So it's going to scroll through a whole bunch of stuff. It'll give a bunch of warnings as well. That doesn't necessarily mean that anything wrong has happened. These are the URLs of these machines here. So there should be 12 of them plus the master because that's what I started up. So it's going to be copying a whole bunch of files over so it can install the software, setting up the disk, etc., etc. Eventually you'll see that here it's copying over the various pieces of the Spark setup, and it'll say that it's basically installing the software and configuring things. So it's basically going through all this setup. And eventually, after it's done all that, hopefully you won't have seen any errors. There will be, let's see, where do I want to get to here? Eventually, at the end of the day, after all of this, you'll get down to something that looks like this, and it'll say, okay, I don't think you need to worry about this failed, because every time I've done this, it's done that. I don't know if anyone wants to comment on that. But eventually, it'll get back here, And it'll say, okay, a Spark standalone cluster has started at this location, and it'll say done over here. And at this point, I'm back on my laptop. Okay, this has all happened remotely. I'm sitting here at the command line at the Unix prompt for my laptop, and I'm going to again invoke the Spark script. Except this time, instead of saying launch, which I had up there, it said launch towards the end. This time, I'm going to say login, and I'm going to tell it the name of this cluster, which in this case is going to be Spark VM-Paciorek because I put my name in there. And then once I do that login, you could actually just, if you figure out what the URL is of the master node, which is basically just this here, you could just SSH into that directly, just a usual SSH in, as long as you specify your private SSH key. But you can also use the login feature of the Spark script. And then once you do that, you'll see that you're now logged into this Amazon-based Linux image, and you're here at this prompt on the master. So you're now sitting here, okay? And you're now the root user of this Linux server that's running in the cloud. So you can basically do whatever you want there, and Spark is meant for you to run basically everything as root. Yeah.
So Amazon is providing this to everyone in the world?
No. What Amazon is providing to folks who asked me to be given access to this and who are Berkeley folks is $5,000 in credits to run to churn through some CPU cycles. So that's what I gave out as accounts to you guys. So over the next couple weeks, you guys can use those of you who I gave out accounts to. Otherwise, you could sign up for your own Amazon account, get the credentials, get the SSH keys set up, and do the same thing. But you'd then be paying for the cycles.
Okay. Where do we get these accounts?
If you go to aws.amazon.com, you can basically go through a whole...
I think there might be some... Were there some provided through the workshop that I'd read?
Yeah, that's what I was saying to him. That if you... In the original email, there was a link to go in and give me your information, and then we set up accounts for you. So if you're affiliated with Berkeley, if you have an @berkeley.edu email address, some of you already did this. Anybody who still wants to get one of those accounts can go to that link, sign up, and I'll provision a few more accounts over the next few days.
The email, but is it on the web page? Because I don't think I have access to that email.
I guess I should add it to the web page. I had just put it in the email.
We must have storage limits also, right?
Storage.
We're going to need to transfer files there if we want to process those files.
Yeah, it's not going to be that much, so I don't think that will come into play.
Oh, but I'm saying if I wanted to use this for myself.
Oh yeah, no, I don't want you to be running up huge costs and doing huge amounts of processing here. If you have a modest-sized data set that you want to try out with this, and a modest amount of computing you want to do with it, that's fine. But I wouldn't want you, uploading and downloading 5 terabytes of data and trying to run 100 instances at once for 2 weeks or something like that. So yeah, everybody should be trying to be a good citizen here.
Well, if we wanted to do that, how would we do it?
Well, then you would sign up for your own Amazon account, link a credit card to that Amazon account, and then you could basically more or less follow these instructions.
Does Spark only work through Amazon? Or?
No, Spark doesn't only work through Amazon, but this Spark EC2 script, which makes it easy to start up the instances and install the software, is set up for Amazon's EC2. Okay. You could start up a Google Compute Engine cluster and install this. Yeah. Or if you had your own cluster, you
talk to the cluster admin.
Yeah, right. You could install the Spark software. Yeah.
And there's a Berkeley Research Computing Group. So you should tell them that you really want to use Spark on their.
Okay, I'll tell the nurse.
That might be harder herself. Yeah.
There's a current effort to get Spark working on the nurse machines, but that's something that's under development for research.
Oh,
okay. Yeah.
So they're working on that actively, but it's not finished yet.
Okay.
Well, my group has.
I'm also involved in the Berkeley Research Computing, so if you're interested in doing it at Berkeley, you could also talk to me, and I have contacts amongst those folks as well. Okay, so what am I doing here? I'm on the master node. I'm going to do a wget to download a big tarball with all the airline data from my website where I posted it. And I'm then so that's downloading it onto the disk of the master node, just the regular disk that you would access via usual Linux commands. I'm then going to untar that big file. It's going to unzip. It's going to untar each of these files, one per year of the airline data. They're still in a zip format, this bzip2 format. And then what I'm going to do, then what I did, was that what I now need to do is get the data from the local disk of the master node into the Hadoop distributed file system. So basically, I need to transfer the data from the master to the disk attached to each of the workers. And so there's basically a distributed file system set up across all of this disk, where the data is going to get partitioned, is going to get sent out to the disk in a distributed manner. So you're basically treating the local disk of these machines as one collective file system. So that is done manipulating the HDFS that is basically sitting on top of these local disks. Is done with these commands that look like this. It's basically Hadoop fs, then a minus, and then various particular commands that you want to execute. And many of these, like ls or mkdir, are basically Unix commands. They're basically just the Hadoop file system version of those. But you need to preface it with this bit. So I'm going to make a directory /data/data and then /data/airline on the distributed file system. And then I'm going to invoke this copy from local command. And what that means is copy from local means copy from the local disk on the master to the HDFS. Okay. So I'm going to copy it from the local on the master. I happen to put it on /mount on the master to that /data/airline that I just made on the Hadoop distributed file system. Okay, so that's going to copy it. In this case, I'm just copying the first 3 of those 20 or so airline yearly files, because I just want to do this on a subset of the data for this particular exercise. And now if I do Hadoop fs and then ls of /data/airline, what I see is that I now have 3 files on the Hadoop distributed file system. This is their sizes, and I can now work with them from Hadoop.
So one question. So you have them zipped.
Yep.
Would they get just? Is it just easy for the system to unzip it, or you have to unzip it to actually?
Once I'm in Spark, I'm going to read in directly from the zip files without manually unzipping them.
Yeah. So my question is, for example, I'm just a little bit familiar with Hadoop and not with this. That I think in Hadoop, unless you have a particular way of zipping them, then one of these guys will go to one master because they have no way of like dividing them.
Right.
Is
So
that the
what? Yeah.
case?
So if we went and looked at this local disk, I think what we would see is that 1987 was on one disk, 1988 was on another, 1989 was on another. So they're not very well balanced across the drives. At the
I
moment.
see. So if you normally you will have to unzip it so that they could be even kind of divided or.
Well, I'm going to worry about the balancing once I get into Spark rather than at this stage, and
Okay.
you'll see that. Yeah.
Okay, thanks.
Right.
You answered my question.
Okay.
Mm-hmm.
Okay. So then, where am I here? Okay. So it turns out when I was doing this, I exited, I re-entered. I'm not sure if I'm going to say too much. Oh, okay. So then, the actual executables for doing the Hadoop file system stuff, the executables live in root ephemeral HDFS bin, and the Spark executables live in root Spark bin, so I'm adding them to my Unix path so I can just call PySpark directly. And then I start up PySpark. And what happens when I do that is it basically gives me back a whole bunch of logging information about from the instantiation of this Spark context and of the Spark instance. So you'll see a bunch of this. I don't actually understand exactly what all of that means. In this case, there was an error. I'm also not quite sure what happened there. So I think I'm going to switch over to my other window, which seemed like it was working okay. And we'll sort of work through the demo from there. So basically what I've done so far here is, where are we here? So we've started up we have gotten the data onto the master node. I will also comment here that let's see, what else did I want to say here? Oh, okay. So another thing, if you wanted to copy directly from Amazon's S3 service, where there are a lot of data sets living, you can do that too. You're going to need to start up the Hadoop MapReduce tasks or workers. And so you'll need to actually invoke those processes with this start MapReduce because they're not already started by default. And then, sort of, for example, if you wanted to download the Hadoop n-gram data, which is basically the word co-occurrence data in this big corpus of documents or books, I guess maybe it was. Here again, I'm on the master here. I'm going to make a directory /data ngrams on the distributed file system, and then I'm going to do a distributed copy from S3 into the HDFS. So I'm going to bypass the step of what I did before of copying onto the master and then copying onto the HDFS. And instead, from the master, I'm going to say, go get the data from S3 and copy it directly into the distributed file system. And I'm going to do that in a parallelized way so that it hopefully should happen faster than this case where I was copying everything from the master and then out to the worker nodes. In this case, you have to tell it your Amazon credentials to get that to work. Okay. Any other questions?
That was my question.
Okay. Yeah. Right, because you could see it would be a bottleneck if you have a terabyte of data that you need to copy onto the master, and then you need to copy the terabyte of data into the HDFS. So this is one way around it. I imagine that there are others. Okay, so the idea of Spark is basically that Hadoop is basically working with stuff. Yeah, Eugene.
Regarding the keys and the login information, is there any kind of tell Spark or Hadoop not to read them from the command line, like read the file somewhere? This is stored in your history. So my key, you run this command, it's stored in your history. So your key is out there, plain text in the history file.
Yeah, I think there is.
There's some strange way to not leave it in your history. You can get prompted for it, or you can stick it in like a secret file.
Okay, so the idea of Spark, as opposed to doing MapReduce through the standard Hadoop infrastructure that's been out there for whatever, a decade now, is that Spark tries to do as much as possible in memory. And so the idea is that you've got we've got this Hadoop distributed file system where we've got the data distributed across disk. You can imagine on each of the workers we also have a chunk of memory, of RAM, for each of those workers. So the idea is that as much as we can, we want to load the data from the HDFS into memory in this collective fashion across the memory of the different nodes. And if the data set is small enough that it fits in the collective memory of the workers, it's going to be much faster to work with than if we have to do a lot of stuff like you would with Hadoop, where you're basically reading and writing from between disk and memory. So the idea is we're going to try and keep stuff in memory as much as possible, and that's going to allow us to do faster, iterative kinds of work. So that's sort of one of the big principles here. Okay, so if we wanted to read data into Spark from the distributed file system, so now we're basically talking about reading from here into the working processes that are going on the working Spark processes that are going on the worker nodes. One way we can do that is, this is our first PySpark command. So this is now in Python, but using the methods and the objects that are provided for us from Spark. So the SC object is a Spark context object, and that basically contains the meta information about this Spark context, about the current working Spark process. So this text file is a Python method that gets applied to the SC object, and then we're going to pass it an argument that says, where am I going to read the data in from? So it's going to read the data in from /data/airline on the HDFS. It's going to read it into an object called lines, and this lines is a distributed data set. It's an object that basically encapsulates the data that has been read in off of the HDFS and is now considered to be a single data set. But that single data set is distributed across memory on the different workers. So, and then we can start doing things with this data set. So the lines is now my data set. I can now apply the Spark methods to that data set to do things. Like the simplest thing I could do is say, count how many elements there are in my data set. So that would be applying the count method to the lines object and with no arguments. Okay. So the idea is if we went back and looked at, let's see, I'm going back to the master. Here are my files. I think I can do less on a bzip file and have it return something intelligent. Yeah. So this is actually what the data set looks like. It's just lines, one corresponding to every one of those flights. So there was a flight in 1987 from San Diego to San Francisco on whatever the PS airline was, Pacific Southwest maybe, if I remember my old airlines. And then a bunch of information about delays and departure times and things like that. So when Spark reads in, when Spark does that sc.text file on the data set, it's basically treating every line as an element or an observation in my data set, including the header row here. It's not magically understanding that that's a header row. It's just treating every line as a piece of data, and that's the observation. And it's just going to be in this text format. So we're going to have to do a bunch of processing to do anything mathematical with it. Okay, so I've already run a few commands here, so let's just page up or toggle up and we can see what I've run. So I ran, what I did here, is this too low for people to see or can everybody see that? Okay. So I ran the sc.text file, ignore this for the moment, to read things in, but then I did a couple more things. I applied the repartition method, and I said repartition it into 48 slices or partitions or chunks. And that gets to Janet's point that originally when I just had the three 1987, 88, and 89 data files, that would basically get read in off of disk, and I would basically just have 3 chunks of data. But I've got 12 workers. Each of those workers has 2 CPUs, so I basically have 24 CPUs that could be doing work. But the CPUs, each CPU is going to work on a particular partition or chunk. So I want to have at least as many partitions of the data set in memory as I have CPUs to work on them. And usually I think the rule of thumb is that you actually have maybe 2 to 4 partitions per CPU, and that will help with load balancing across the different tasks. So I'm going to take my 3 chunks, the one per each year, and I'm going to repartition it into 48 chunks so that they're more balanced in terms of being distributed across the CPUs, both in terms of using memory and in terms of doing the processing on each of the chunks. So that repartitioning I already did. And once I do that, unfortunately I'm running this in screen here and I can't seem to scroll up to see exactly the messages I got. But when I do that, it's basically going to spit back a whole bunch of logging information to me that's basically saying, first it'll say it's working through 3 tasks, which are basically to deal with the original 3 data files. And then it's going to say it's basically creating 48 partitions to my data set. And it's going to have a whole bunch of logging information. And henceforth, basically whenever we run a command to do another operation on this lines data set, it's going to give us some logging information that's going to say starting task 0 of 48 or 0 of 47, or maybe it starts from 1. Starting task 1 of 48, starting task 2 of 48, etc., etc. Finishing task 33 of 48. And it'll tell you the progress as it's working through the different partitions and doing the operations.
That partitioning, I guess, happens in memory, right? It's not writing any files to disk when it does that. Is there a way to interact with the Hadoop file system to do that repartitioning in advance or something like that?
I'm not sure. Jay?
You could do that once, like load everything into Spark, repartition it, and save it back to HDFS.
Right,
and
okay.
You pay the one-time cost.
And when you save it to HDFS, it's smart that if you have 48 files and 48 workers, it will put 1 file per worker. How does it decide? Does it make any guarantees about that?
So the partitioning is a property of the RDD, and so you can like say, let's say you read it in and it's only 4 partitions, and then you repartition it to 48, and then you save it, and it'll still be 48 partitions. So the structure gets preserved when it's read or written to disk.
You see, and a partition is guaranteed to be contained entirely on a single worker?
Yeah. Okay. Yeah. You can think of it as like a contiguous block of memory. That's that.
Yeah. So then if you close down Spark, but the HDFS was still sitting there, you could then reopen Spark and then load that in, and it would be partitioned in the way that you wanted. Yeah.
Why do you need to repartition?
Basically, it's a load balancing and a memory balancing thing. Otherwise, in our case, we'd have the original 3 data sets are sitting on disk on 3 of the workers. We just have 3 partitions. We'd only be able to use 3 CPUs at once.
We have 48 then? Is that what you're saying?
Now once I run this, we now have 48 partitions, and I can run, since I have 24 CPUs, it's basically going to start up 24 tasks. As those finish, it's going to sequentially start the individual remaining tasks. Okay, and the cache basically tells Spark that I'm going to use this lines data set later on, so keep it in memory so that I could, and don't, yeah, so basically it's an indication to Spark that I want to keep this in memory because I'm going to operate it on it later on. Okay, so then for example I could do this lines.count. So let's do lines.count, and I'm going to assign it just into a Python object. This Python object n is just a Python object that's living on my master node in my Python session. So there's nothing distributed about it. I'm just collecting the information back from the worker processes as a Python object. So if we do that, you can see it's going through this thing about starting and finishing tasks, 42 of 48, 47 of 48, 48 of 48. It returns back to the Python prompt, tells us that took about 5 seconds to count up how many there were. And now if I look at n, it says, okay, there are like 11 million observations in this data set, 11 million rows. So let's see, where am I here? Okay, you can also read directly off of S3, Amazon's S3, and so that syntax would look something like that there. What else do I want to say here? This is repartitioning. Okay, so let's talk about subsetting. So suppose all that you wanted to do in Spark was you had this huge data set and you just want to use it to basically pull out chunks of your data set that you're then going to use to analyze elsewhere, presuming that the chunks are then small enough to just work with on a single machine. So here's another method that we can apply to one of these distributed data sets, which is the filter method. So I'm going to take my data set, I'm going to apply the filter method to it, and I could in here pass in a function, a named function, but this is just going to be an anonymous function, which in Python is called a lambda function. This is just like if you're using R, it's just like passing in a function on the fly to lapply or to sapply. So this function takes as an argument, the argument is going to be named line. It's going to split up the line based on the commas. Because it's comma delimited, it's going to pull out the 17th field because Python is 0 indexed. And it's going to ask whether SFO is in that 17th value. And if it is, it's going to return either a true or a 1, and if it's not, a false or a 0. And that's, so the filter method needs a function that returns 0s and 1s, trues and falses to be able to do the filtering. Okay. And then I'm going to, so that filtering is going to create a new distributed data set that I'm going to call SFO lines, and I'm also going to cache that distributed data set. And then I've got this new data set. I can do anything that I want with that new data set. I could, for example, count the number of lines, the number of observations in that data set as well. So if we go ahead and do that on the fly here. Okay. The other thing I should mention, which I didn't get a chance to point out before, is if I had just done the okay, so it says there are 293,000 flights in the SFO subset. If I had just done this step here without doing the count step, what it probably would have done was returned to the Python prompt very quickly, and that's because Spark uses lazy evaluation. So until you actually tell it to do something where you basically really tell it that you need some result back, it's basically not going to go and do it until you until it sort of gets something that it really needs to do to give you a result back. So in some cases it may be hard to time how fast something is, because you'll say go and it'll return later, a millisecond later, it won't have really done anything, and then you'll do another operation that makes it do something, and then it'll be doing both of those operations, and it'll be a little bit hard. It's maybe hard to sort of disentangle how fast the first one and the second one were. Yeah.
So you had 48 chunks. Now you have 48 smaller chunks. Is that right?
Yes, that should be right.
And if your data set was kind of sorted, then you would have one really big one and the rest empty.
I think that's probably right. Yeah. Yeah, so you could potentially do a repartition of the SFO lines data set to redistribute things. Of course, there's a fair amount of cost to that, because you can imagine if almost all of the SFO data were living in memory on this worker, you're now needing to do all the communication to basically spread it across all of the other workers across the nodes.
When you partition by default, does it do it randomly?
I don't know how it does it.
Basically, yeah. It's by the hash function. So it's deterministic, but not really meaningful.
How random? Can you trust that it's random? For example, could you do inference based on it being random? Could you use it? You know what I mean? You know what I'm asking? Like, could you treat it like a subsample estimator? Could you do checkpoints with it?
I wouldn't assume any statistical guarantees. It's like for purely computational reasons. So if it's more convenient, they might change it to something that's non-uniform, or that informs your statistical procedure.
Could you generate your own random numbers and force it to do it? And
You can impose it or have it choose a random permutation or something.
Okay, so I haven't done that yet. So let's go back and I want to take the data that I want to take the distributed data set that I just made and I want to save it to the HDFS. And then I want to get it from the HDFS back to the master so that I could just do something on the master or I could get it back to my local machine. So I'm reversing the steps I did before. So I'm going to get it from Spark, from the distributed data set on Spark. I'm going to put it into the HDFS. I'm going to transfer it back to the master. And then from there I can do whatever I want with it. So from Spark, I'm going to take the distributed data set. I'm going to use the save as text file method. I'm going to save it to this location on the HDFS. And so once I do that, it's again going to churn through the 48 processes. It'll came back pretty quickly, and now I should be able to go back to, now I'm back on the master node at the Unix prompt. I'm going to do a Hadoop file system ls on data/airline./SFO. And now what you see is basically what is sitting in a distributed fashion on the distributed file system is all of these different parts to that data set. Okay? So I've got parts, they probably start with 0000 and they go up to 00047 because there should be 48 of them. So I could at this point simply, do I have this in here somewhere? I guess I didn't actually. Oh yeah, I just sort of indicate. I just sort of made a reference to it. I could do a copy to local before I'd done a copy from local from the master. I could do a copy to local to get it back from the HDFS onto the master. Once I get it back onto the master, it's still going to be in those 48 chunks. So at that point, I would either need to use Unix tools like cat to get it all together into a single file, or you can probably imagine what I'm going to suggest next, which is basically following along with sort of the line of discussion that we were just talking about. I could take the SFO lines and I could repartition that into one partition. Right? So the SFO lines is right now in 48 partitions. I could do a repartition and tell it to put it in one partition. Then it's only going to be sitting in one file on one of the disks, and then when I do the copy to local to get it back to the master, then I just have a single file, and that's going to be easy to work with. Okay. Let's see. Questions or comments at this point? Yeah.
Can I just ask a question about the SSH key? So the one that we're supposed to use to get into, or to set up the master and the slaves is it the .pem file that we
need? Yeah, so you'll need to, when you are, so that, the public version of that key is on the, is logged on the Amazon side of things. And you're now putting the private version of that key, the standard place to put it would be to take that file. Here I called it .rsa. That was probably a little confusing because the one that I'm using is .rsa. But this whole thing here is you would put that .pem file, by convention you put it in your .ssh folder in your home directory on your local machine, and then with the -i flag you would reference to it. And then you have to also tell the Spark EC2 script what's the name of this key. And there I have some instructions, just what that name actually, what the syntax of that name has to look like exactly.
And is there particular permissions? Like I tried 400 and 600, and it keeps saying that like it can't find the key.
If it can't find it, then you probably haven't put the key in this place where you're then referring to it. If the permissions are wrong, they should be 400. If the Unix permissions are not 400, it will probably return error saying that those permissions should be set to be more restrictive. And the 400 just means that it's basically read only to you and not to anybody else on the machine. Yeah, question.
In terms of the repartitioning, why did you do 192? Just so I can understand.
Yeah, so that was when I was doing, for the what's actually hard-coded into the HTML is when I had the full airline data set with the 22 years.
Yes.
And then the idea was, I basically wanted to get it to be at least a few partitions per CPU. I had 24 CPUs, and I decided to make 8 partitions per CPU, so I took 24 times 8.
Is there any rule of thumb there, just so...
I think what I've seen is the rule of thumb, and Jay can weigh in if he wants to say something different, is something like 2 to 4 per CPU. So in this case, this might have been kind of overkill to have 8.
The related question is like, well, if you have 10 gigabytes of data, what could be the meaningful number of clusters, or which size? So, should we just count in the how much memory each cluster have? Or?
I would guess that you want it to be such that an individual partition can fit in memory on an individual worker, and I guess if you had 2 CPUs per worker, you'd probably want to have enough so that 2 of these could fit in memory at one time.
Yeah.
Does that intuition sound about right?
Yeah, I mean, ultimately it's kind of an art to choose these sizes. So at one extreme we could have one element in each partition, but then the per partition overhead starts to be the dominant thing. On the other hand, if you put all the elements into a single partition, then all the work has to go to a single CPU, and you don't get good load balancing. So it's somewhere in the middle where you keep all the workers busy, but the per partition overhead isn't too high.
Yeah. So do you do something like, I know each computer has this memory multiplied by whatever, and so that I get 10 gigabytes? Is that the math?
Sorry,
yeah, I'm talking about, you have 10 gigabytes of data, no? And suppose I can start as many clusters as I want. I just want to make it the best I could.
So I think, one rule of thumb there would be if you have the resources in terms of money and whatnot to start up many nodes, then if you have 100 gigabytes or a terabyte, you might want to start with a very large number of nodes such that you can basically fit the entire data set in the collective memory across all of the nodes.
Yeah, okay. Just that simple,
Yeah.
You mentioned at the end when you want to repartition all the SFO data into one partition, right? And then move it from your
from the
slave
HDFS,
to your master. What if the memory in one work is not large enough for your all that?
Yeah, I mean, I guess in that case, then you might keep it in the distributed fashion, copy it back to the master, and then if you really wanted to make it into one big file on disk on the master, you could use some Unix tools at that point to basically concatenate it all together.
But if the memory is not large enough and you're trying to repartition to one, what's going to happen?
Then I believe what will happen is that, let's see, I think it's then going to start using disk very intensively and basically having to go back and forth between memory and disk.
Sorry, what was the question? To repartition to a single partition?
What if that single partition were more than the memory of a given worker, and I tried to repartition into one partition?
One partition has to be able to fit memory at a minimum. So you can't have like a 10 terabyte partition. But there, I can't really think of a use case where we really want everything to be in the same partition. Because you can have one file that's multiple partitions, so you can still be like an order sequence, just split up into like 100 byte chunks or something.
Yeah, I guess my use case was I was trying to collect it back to the master in a convenient form. But if we were going to do anything else with it in Spark, there's no reason to repartition it to one partition. Okay, so let's see where we are here. So far we basically just sort of dealt with sort of getting things set up. So let me talk a little bit about doing something a little bit more interesting. So suppose we want to do a little bit of sort of stratification, doing some stuff within strata or different clusters of the data. So this is basically our sort of first sort of MapReduce operation here. So the idea is, and I'll say a little more generally about what MapReduce is in a few minutes, but I just want to give you an example first, is I'm going to take my original lines data set, so I'm backing back out not to the SFO subset, but to the full 1987 through 1989 data. I'm going to apply the map method to that using this create key value function. So basically what I'm going to do when I do a map is I'm going to take the data set and I'm going to do a transformation of it to make a new data set. And in general, that will often be the form of, I'm going to take each observation in the data set and transform it into a new observation in some fashion. So this function here that I tell it to use here is the function that is going to transform each observation into the new observation in the new distributed data set. So in this case, all I'm doing is I am splitting up the line of the CSV, the comma-separated text data, and I'm combining with a minus, just as a text string, the departure airport and the arrival airport. Okay. And then that's going to be the key. So the first thing that I return, I'm basically returning a Python tuple or a Python list here. The key is going to be the first element, and then I'm going to have some value as the second element. In this case, I'm just putting a 1 in because I'm just going to end up counting up these things because I want to count the number of flights between each pair of airports. But this could be arbitrarily complicated, what I want to put in as the value here. This could be a list of things. I think it could be sort of anything. It could be a dictionary. It could be a whole bunch of other stuff. So I'm going to do this mapping to create a new distributed data set, and then we're going to use a new method that we haven't seen yet, which is called reduce by key. And that's basically going to group all of the things that's going to group by the key value that I've created. So it's going to group by the arrival-departure pairs. And it's going to do a reduction of all of the values that correspond to a given common key. And in this case, the reduction is just going to be to add the values. So the reduction operators have to be basically very simple operators that are associative and commutative. So it can't matter what order you do it in, and it can't matter which pairs of things you do things to, because all of this parallel processing is basically just, it gets 2 arbitrary elements and then has to combine them together, and then it gets another 2, and it's basically just combining in pairs. So taking a max or doing addition is a natural thing to do with a reduction, but as we'll see in a minute, doing a median would not be something that you could easily do in this way. Yeah?
So it always kind of assumes that you don't care about the ordering of our rows in the data set.
Right.
What if we did? Is there a way to kind of impose time series conception through the partitioning and then calculating the running sum or something like that?
You can sort in RDD, and the order will be preserved as long as your transformation still preserves the order.
Right, I think the question then would be what you then do with it that would be able to operate in this kind of paradigm.
Well, I had something like a window, like a running cumulative sum so I can physically do windows and chunks. And I guess
right. Again, I think the challenge would be how to fit it into this paradigm of this map and reduce operations. And maybe for certain things you might be able to do it, but it might take some thinking. Yeah. Yeah. How to,
so in your map function, you can return a tuple of key value pairs per observation. Like here, you just have a 1-to-1.
Yeah, there's an operator, a method called flatmap, which allows you to return multiple observations, and I think that might be what you would do here. Does that sound right? Okay. Okay, so then this reduce by key actually isn't yet we're going to return anything to the master. All it does is create a new distributed data set, 1 value per unique key. So now I'm going to have each arrival-departure key, each pair, each key, and I'm going to have a count, and that's going to be a distributed data set. If I wanted to get that back into the master Python session, then I have to call the collect method to basically pull it back to the master from the workers. So let's go ahead and run this. And where am I here? Okay, so again, it's going to churn through the 48 tasks because I have the 48 partitions. Hopefully that'll go pretty quickly. I've now written a little bit more Python code that I'm basically just executing as just standard Python code on the master, where I'm just trying to find which is the airline route amongst all the domestic U.S. routes that has the most flights in this time period. Anyone want to make a guess? Yeah, good. A very local one. So a little for loop in Python, and indeed, the maximum is SFO to LAX, or in this case, the other direction. And in those 3-year period, there are 48,000 flights between those 2 cities, or between those 2 airports. If we just typed in, let's see, what else do I want to say here? if you were actually really just counting up things by key, this would be a more efficient way to do it. There's a count by key method. Here I just wanted to illustrate the use of the reduction by key, so that's why I did it in a more sort of verbose manner there. Okay. So another thing that I found is oftentimes, especially as you're getting used to this, you'll try and do something and it'll return this very long, it'll have all the logging information, and then embedded in the logging information will be a bunch of error messages. And you'll be like, what the hell is going on here? Sometimes that might be something going on with Spark, but oftentimes that's because you've got a bug in your Python code. And so sometimes you can sort of burrow into that logging and the error messages and realize, okay, there's the line that has that indicates the error in my Python code. The thing that I found is very useful is to do something like this, which is each of these map operations is going to operate row by row or observation by observation on the elements of your distributed data set. So let's go ahead and just pull one of them back onto the master. So here's one line. This is just one of my observations. I can now just run my Python function, the function that I was using in the map method. I can just run it on this object and just check to see if it works the way that I think it should work. So in this case, the create key value is the function that I'm using in my map. So let me just try and apply that function to this individual observation. And it's going to give an error because at the moment it's seeing this as a Python list within which there's a Python string. So I basically need to, that's fine from the perspective of the mapping and the distributed data set, but in order to actually get this to work here, I actually need to tell it explicitly to pull out the 0th element of this list, which is just the string, and then this will work. This function should work on that, and indeed it returns back what I expect, which is it pulls out the 2 airports, LaGuardia and Syracuse, I guess, in this case, and so that's going to be the key, and this is going to be the value, which is just a 1.
Where does that collect computation happen? Does it happen on the masters or on the workers? That is, where does the reduce happen?
I think the reduce is happening on the workers. Is that right? Yeah. So it's happening in a distributed fashion.
There's a final reduction on your local machine, but it's like
with the
think of that as, yeah, but most of the work is done.
Okay, so as I was working through this, I found this to be very handy, that I could pull back an individual element or an individual set of elements, make sure that my Python function worked appropriately, either in the map context or if I create a, did I do this up here? Oh, I think oh, here we go, okay. So here I'm not doing the whole pipeline of operations that I did up here. So here I had a whole pipeline of operations. I did a map, then I did a reduce by key, then I did a collect. I'm just going to do the first one in that pipeline of operations. So I'm going to do the map, and then I'm going to consider that as a distributed data set. And I'm going to take back 2 observations, which are going to be 2 key value pairs, into this thing I called 2 key values, which is just going to be on my master Python process. You can see what those are. That was a flight from somewhere to Pittsburgh and from LAX to Indianapolis or something. And now I could actually do, I could try out my reduce by key on that, what am I doing here? I'm getting, I guess I basically wanted to see what was sort of the interim result, and then I wanted to make sure that the individual elements of doing the reduce were what I was expecting. So, sorry, I'm not quite sure what I was thinking there, but the basic idea is I'm trying to be able to basically piece apart the individual pieces and be able to do some debugging in this way.
On the line where you're assigning key values, the cache function that just lets you save the result of the map function, is that the reason you have that? Or?
Yeah, the idea is to tell Spark that I'm going to do some subsequent operations and to keep it in memory so that I can do those subsequent operations more quickly.
Do it and it wouldn't return anything to you. Is that it?
Wait, say that again?
It would do the mapping, but it would return anything to you. I'm just trying to understand why.
Well, regardless of whether I have the cache here, I'm still going to have my key values distributed data set that I could then do operations on. But the idea is to give Spark an indication that I want to keep that in memory because I'm going to work with it again very, very soon.
The rule of thumb is if you're going to use an RDD more than once, cache it. So if you're only going to use it to compute one value, then the RDD itself can be thrown away as soon as the result of the compute.
RDD.
So it's like the distributed data distributed.
That leads very nicely into exactly what I was going to say next. So, so we've seen a few examples of things. I'm going to define a few terms a little bit more carefully here, and then we'll do a couple more examples, and then we'll quit. So what I've been calling distributed data sets in Spark terminology are called RDDs, which are resilient distributed data sets. And as we've seen, basically, all of these operations that we're doing are we're taking an RDD and applying a method to it, and that either produces another RDD or it produces a result that exists back on the master node just in our Python session. We've already seen caching, which is this idea of making sure that it is cached in memory so that we can operate on that RDD quickly when we next want to operate on it. The other thing I should mention here is, and I indicated this further up, there are a bunch of interfaces, of web interfaces that are set up by the HDFS and by Spark for you to go in and sort of see what's going on. So if you just in a web browser go to the URL of the master node :50070, this gives you a little interface to tell you what's going on the HDFS. So this says, okay, there's 9 or 10 terabytes across all of this disk. You happen to be using not very much of it here because you have a small data set, so this is how much space you have left, and so on and so forth. So you can get a sense of what's going on collectively on the HDFS there. Probably more interesting for our purposes, this is the Spark interface, which is at that same URL :4040, and it gives us a few different tabs up here, so we can see basically what are the stages of. I think I need to refresh this. What are the different stages of operations that have been done so far? So if we go back, we can see, okay, I started with reading this, I know this is small in the back, I started with reading the data in, and there was a repartition. There were 3 tasks at that point. Well, originally there were 3 tasks. I did a repartition. At this point, there were then 48 tasks. I did some of those counts. I ran a few jobs. I guess those were some of the various subsetting and whatnot. I saved as a text file. Those are all the different tasks that I basically, or processes that I basically started up. And if I look in storage, I'll see that it indicates the different RDDs that are cached in memory. And you can see this must be my primary one. This is the one taking up the 400 megabytes or so. Okay. Yeah.
So if you have a data set that is 50 gigabytes and you have 10 gigabytes over your 2, let's say you have 2 workers, 10 gigabytes over them.
Of RAM?
Of RAM. Are you not able to do Spark over those 2?
No, you can. I mean, you need to have enough space on the disk such that you could store them on disk. And then when you're working with the partitions, you want to make sure that each partition can fit in memory. So you'd want to set up enough.
So you wouldn't be able to load the whole data set into memory.
Right. In that case, you wouldn't. Yeah. Right.
So
either
some sort of like virtual object, you need to just go ahead and like do the MapReduce and get to a data set that would fit in the collective memory.
Well, it's fine to do that. It's just going to take more time because what's going to happen is you're going to the workers are basically going to be you're going to have these partitions. The partitions are going to get written to disk, and as it tries to work through the partitions, it's going to be reading and writing from disk and moving a partition into memory, doing something with it, moving it out of memory, moving the next partition into memory, and doing that. So it's going to be slower than if you could fit all of the partitions in memory at once and cache them all in memory. If you had enough money.
Pretty common. Like a lot of times, data sets don't fit in memory.
Right.
But you can still like process one partition at a time, and because you're only taking one pass over the data, it's okay.
Right. It would hurt you if you were doing an iterative thing where you're doing many passes, which we'll see in some of the model fitting. Okay, so let's see here. Okay, so we've talked about partitions, repartitioning. We've basically talked about MapReduce. So basically, I'll say a few more words about this. So MapReduce is basically, it's sort of an algorithm, but it's really sort of more of a meta-algorithm, where you take the algorithm that you want to do and you try and see if you can express it in this form of these map steps, which are these transformations from one data set to another form of the data set. and these reduce steps, which are basically aggregations, which could be done by key or could be an aggregation applied to the entire data set that aggregates down into some smaller summary measure of the data. And then you can iterate across this. You could have a pipeline of a whole bunch of map steps and then a reduce, and then you could have this wrapped in a loop where you're iterating, and maybe the result of the reduction you then send back out to all the workers. And then you have another set of map steps and a reduce where the new map steps are relying on sort of the summary statistic that you computed in the previous iteration. And we'll see some examples of that. So you can sort of combine all these things together. And if you can express your algorithm in that sort of set of operations, then you could do it in this context. Yeah.
What was that master debugging URL? That was like, was that just master nodes URL 45000?
Yeah, it was the master nodes URL, and then for Spark it's :4040. It's all in the HTML file, okay. But for Spark it's 4040, and for the HDFS it's 570. Okay. So let me show you a couple more examples quickly, and then we'll quit for the day. So we might want to see a reduction where we do where our summary measure is to calculate a mean. That would be an obvious thing to do. You might want to take your huge data set, do some collapsing where the collapsing is you get a summary statistic for each stratum in your data set. So here, for example, I'm going to define a stratum as I'm going to make a key where I join together with a minus the I think this is the airline, the 8th element of my observation line, the airline, the month, the departure, and the arrival airports. So I'm basically going to say, what's the mean delay for every combination of airline, airport, airport, and month? Okay. So I'm going to create the key after I've split up my CSV line. I'm then going to make sure to screen out cases where there's a missing value for the delay, which is the 15th field. Or if it's a header row, I'm going to screen that out as well, and I'm going to detect that by saying if the first value is just the string year, that means it's one of these header rows. And if that's the case, then the key is going to be 0, and I'm going to say this is an invalid data point. That's what my valid equals 0 is going to mean. Otherwise, if it's valid, I'm going to say the delay is converting that string value to a float, and I'm going to say my valid value, my valid element is a 1. And so then I'm going to return a key value pair where the key is this information about the what the stratum is. And the value is this tuple, which is the delay value and whether or not it's a valid value. So key value pair where the value has 2 elements. And now I'm going to write, so that's my mapping function, which I call mapper. So I'm going to do a map function. I'm going to use the map method with my mapper function, apply it to the lines. I'm going to create this new RDD, which are of key value pairs, which is mapped lines. Then I'm going to do a reduce by key on the data set of key value pairs. And I'm going to use this function I call reducer. And what does this do? It's basically going to sum up the total. It's going to sum the departure delays, and it's going to sum the number of valid observations. So as a result, since I put in a 0 for the delay when it was invalid, if I divide later on, if I divide the total by this sum, then I'm going to get the right mean for this. So what do? I guess rather than running this, I guess I'll just show you the results. I do the reduce by key. The result of that is still one of these RDDs. That's this temp. Then I do a collect on that, and I get the results back. And what do they look like? Well, they're the key value pairs where I've got the key, and then this is the aggregate value. This is the aggregation over the values up there. So this is the total sum of the delayed minutes, and this is the total sum of the number of valid flights. So obviously, I can then just go through and with a little bit of Python syntax, I can do some list comprehension and loop over these guys and do 1531 divided by 265 and this divided by this and whatnot to get back the actual mean departure delay for each of these. And once I do that, I get, okay, that for Eastern Airlines in November from Atlanta to Denver, this was the average departure delay. And presumably I could then go take that and do some other statistical analysis on it. But I've gotten it now crunched down into some summary measure. Okay. So So why don't let me just say this one last thing and then we will quit. So this was my attempt to say, well, you know, oftentimes we might not want to do something that naturally fits within this this idea of having a simple reducer that can operate in an associative and commutative way. So this wouldn't necessarily scale the really big data sets, but it works for the full airline data set pretty well. So I said I want to actually compute the median for each of these keys. So I'm going to do the same. I'm going to use the same key value data set with the mapped lines that has these kinds of keys, but I want to compute the median delay instead of the mean delay. So the problem with that is I basically need all of the delays for a given key to be able to compute the median. So how would I go about doing that? Well, the idea is I can actually group all of the data by key. So I'm going to take my RDD, that's the RDD of key value pairs, I'm going to group by key. And what that basically does is it sets it up so that I now have a new RDD of key value pairs, but it's a little bit more complicated because the new RDD is basically, each observation is going to be the key, and then it's going to be an iteratable object that has all of the values associated with that key. So this could be very long, because I might have a lot of observations associated with this key. But as long as it's not too long, I should be able to work with it in this fashion. So that's what group by key will do. And then to the RDD of these of this new kind of set of key value pairs, well, I can certainly count that. I get 186,000 unique key value pairs, so 186,000 unique keys. I'm now going to apply my median function to this RDD, and then I'm going to collect the results back. So what does my median function look like? I basically say if the input that's coming in does have two things, if it does have the key and this second element, which is the iterable object, and if the length of the second piece here, so the first piece because it's 0 indexed, if the length of this is bigger than 0, then basically iterate through all of the values in this iterable object here. So iterate through that with some Python list comprehension. And if, so val is going to be, so val is now, remember these guys are themselves the delay and whether it's valid or not. So each of these elements is just two numbers. So val is going to be that 2-element list. And so I'm going to compute the median over the 0 elements, which are the delays, only if the second element, which is the validity element, is a 1. So the syntax, if you're not familiar with Python and list comprehension, is a little bit convoluted, but just think of it as extracting out only the delays for which valid is equal to 1, and then I'm just going to apply the median, numpy's median function to that. And then as a result, I'm going to return back the key and the median value. So once I do that, I now have a new distributed data set, which is a set of keys and a set of median values, and I'm just going to collect that back to the master and look at it. And so it looks like what you would expect. All of the values happen to be integer minutes, and so this particular median function is just computing. It's not doing any sort of interpolation between integer values. It's just returning an integer value for each one of these. And so I get this back at the master. Okay, so why don't we quit there? Let me say a few words about next time for those of you interested in coming back. So what I'll talk about next time is stepping away from this idea of doing a bunch of data processing and thinking about what if we wanted to run some simulations here, so sort of massively parallel simulations across all of the nodes in the cluster. Or what if I wanted to fit statistical models to a data set that's distributed in this way. And so I'll go through both of those. I have a few examples of running some linear regression and lasso model. So basically some iterative fitting. And as I said at the beginning, I'm very open to, if people are interested in particular things, take a look at what I have planned here and send me any comments you have, and I can try and adjust to that. at the bottom I have a few homework problems. So obviously these are optional since no one's forced to be here. But the 0th homework problem was just to try this out for yourself and see if you could recreate what I've done and see if you run into problems or play around, make a few tweaks to it. The first problem is to do something a little bit more complicated and see if you can come up with some Python syntax and some Spark syntax on your own to basically add a new field, a new column, a new variable to one of the data sets. And then the second one is to actually take some of the statistical modeling I have that I'll talk about next week and fit a logistic regression model instead of a linear regression, which is what I show. So if you wanted to play around with that in advance, you could, or you could wait until I go through it next week, and then you could play around with it after next week's thing. The one last thing I want to say is that if you're really interested in this stuff and hearing about it from the pros as opposed to an amateur like me who just learned this in the last few months, the AMP Lab is running something called AMP Camp, which is a 2-day workshop, November 20th and 21st. Unless you have an in with the AMP Lab folks, this is $600, and it may already very well be full, so you might not be able to get in regardless, even if you're willing to spend the money. But they're doing dry runs of some of the talks and the demos for the camp. They're doing dry runs, sorry about this. The dry run of the talks are November 13th, which is next Thursday, so before the next time I may see some of you. From 10 to 4 in Soda, from 10 to 4 in Soda 606. And dry runs of asking people to try out the exercises are November 17th, so a week from Monday. So those are some possibilities if you want to see more of this, hear from some of the pros and see some more advanced functionality as well as some recapping, presumably, of the sorts of things that I've done. So that's all. And if you are trying things out and using the Amazon instances that we've set up and you run into problems, just email me and I will try and help you out.
Sorry, just one last question to actually